Welcome to this Concept Explainer, brought to you by CBSE ScoreLab of ProfSam.com, that is ProfSam.com. Today we are starting a deep dive into Unit 13, Nuclei. Specifically, we'll be looking at atomic masses and the composition of the nucleus. Our mission is to explain this complex topic simply, making sure you understand the structure of the nucleus, how its mass is measured, and of course, keeping it all exam safe. Let's start with a simple question, something you probably noticed in chemistry. You know the atomic mass of chlorine is 35.45 AU. It's not a nice whole number like 35 or 36. Now, if an atom is just made of whole particles, protons, and neutrons, how can its average mass be a decimal? Just seems a bit strange, right?
It really does. I always just assumed it had something to do with electrons or maybe some tiny measurement errors. But if the blocks themselves are whole, why is the final number a fraction?
That is the exact puzzle we're going to solve. And to show you how important these tiny mass differences are, just think about carbon-14 dating. Archaeologists use it to date things like the Dead Sea Scrolls. And their entire method relies on measuring the incredibly tiny mass difference between carbon-12 and carbon-14. The only difference is 2 extra neutrons. But that tiny change makes C14 unstable, and it starts to decay. This property is purely nuclear. It has nothing to do with its chemistry.
Wait, hold on. If C12 and C14 have the same electron structure, their chemistry should be the same.
Exactly.
So how can the nucleus have such a huge effect on its stability, but basically zero effect on how it reacts chemically?
That is the perfect question. And it brings us to an even better example, uranium-235 versus uranium-238. Chemically, they are twins.
Right.
Same electron shells, they form the same compounds. Everything's identical. But, and this is the big but, that tiny difference of just 3 neutrons makes U-235 fissile. It splits easily and powers nuclear reactors. U-238, on the other hand, is much more stable. So this shows us that the nucleus is really the boss when it comes to stability and energy. So let's dive into the core idea. At the center of every atom is this tiny, unbelievably dense nucleus. Inside, you have protons, which define the element, and neutrons. Now, here is the paradox. This is the foundation of all nuclear physics, so listen carefully. The actual measured mass of a nucleus is always a little bit less than the sum of the masses of its individual separate protons and neutrons.
So you're saying if I take all the ingredients, weigh them separately, then put them together to form a nucleus and weigh that the final nucleus is lighter.
Yes.
That sounds like it violates the law of conservation of mass, like mass is just disappearing.
It does seem like that, doesn't it? And before Einstein and EMC ordered it was a huge mystery. Let's use an analogy. Let's call it the marriage paradox. Imagine 2 separate people, each weighing 70 kilograms. Their total mass is 140 kilograms, right?
Right.
Now, they form a very deep, stable bond, our nucleus. If we could measure the mass of their combined system, we'd find it's now, say, 139.5 kilograms. That missing 0.5 kilograms hasn't vanished. It has been converted into the energy of their bond, the energy that holds them together so strongly.
I see. So the missing mass is basically the price that was paid to create that powerful bond.
Exactly. The stronger the bond, the more mass had to be converted into energy. This is what we call binding energy.
And this energy is what keeps the protons from flying apart because of the repulsion.
You've got it. The immense Coulomb repulsion between all those positive protons should tear the nucleus apart. The mass defect, this missing mass, converts into the huge binding energy needed to overcome that repulsion and keep the nucleus stable. Here's a mental image for you. Imagine a hypersensitive scale, really, really sensitive. On one tray, we put 6 separate protons and 6 separate neutrons. On the other tray, we put one single bound carbon-12 nucleus. The side with the bound nucleus would be visibly, fractionally lighter. That mass that seems to have vanished. It's now an aura of force, the binding energy holding that nucleus together.
That's a powerful image. We're always told the nucleus is incredibly dense. I kind of thought the particles were just compressed so much that they lost mass.
That's a really smart connection to make. And the density is just mind-boggling. A 1 centimeter cube of nuclear matter would weigh 100 million tons. But the compression itself isn't the reason for the mass loss. The reason is the energy. When the strong nuclear force pulls the particles together, energy is released. And because of EBC-LC, any release of energy must mean there's a corresponding loss of mass. They are 2 sides of the same coin. We've basically traded a tiny bit of mass for a whole lot of stability. Okay, now that we have the concept, let's look at the formal definitions from insert. I need you to read the definition of the atomic mass unit for us.
Of course. It says, the atomic mass unit, E, is defined as 112th of the mass of the carbon C atom.
Perfect. And what about the components A, Z, and N?
Right. The mass number A is the total number of protons and neutrons. A equals Z plus N. The atomic number Z is the number of protons. Nuclides are shown by the notation X with A as a superscript and Z as a subscript.
Great. So now we can finally solve your original question about chlorine having a mass of 35.47 U. Where does that decimal come from? The answer is in a simple three-step process. Step 1. We have to understand isotopes. Isotopes are atoms of the same element. That means they have the same Z, the same number of protons, so their chemistry is identical, but they have different numbers of neutrons, N, and that means they have different masses.
So what we find in nature isn't just one type of chlorine atom, but a mixture of them.
Exactly right. Which brings us to step 2, the chlorine example. Natural chlorine is a mix of two main isotopes. About 75.4% of it is chlorine-35, and the other 24.6% is the heavier chlorine-37.
Okay, so there's much more of the lighter one.
Yes. And that leads to step 3, the calculation. The mass we see on a periodic table is a weighted average. Since there's 3 times more of the lighter isotope, the average will be much closer to 35 than to 37. When you do the math, 75.4% of 35 plus 24.6% of 37, you get almost exactly 35.47 U. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com. All right, let's do a quick work example. Let's calculate the mass defect for a nitrogen-14 nucleus. That's ERO-N.
Okay, so Z is 7 and A is 14. That means it has 7 protons and 7 neutrons.
Correct. Now, to calculate the mass defect, we can't just use 1 U for a proton and 1 U for a neutron. We need the super precise values. The mass of a free proton, MP, is about 1.00728 U. And a free neutron, M, is slightly heavier at 1.00866 U. So first we calculate the total mass of the separate parts. That's 7 times the proton mass plus 7 times the neutron mass.
Let me see, that would come out to 14.111158 U.
Perfect. Now that's the mass of the ingredients. The experimentally measured mass of the actual bound nitrogen-14 nucleus is 13.999923. So the mass defect to them is the difference. It's 14.11158 minus 13.999923.
Which gives 0.11235 U, a very tiny number.
Tiny, but incredibly significant. That 0.11235 of mass is what got converted into a 104.6 MeV of binding energy. This binding energy, which we'll study in the next session, is the source of all nuclear power, and it all starts with finding this tiny bit of missing mass.
Okay, let's shift gears. We need to talk about some silent killers. These are common misconceptions that can, cost you marks in an exam. Misconception number 1. Students confuse the mass number, A, with the actual atomic mass in U. They think if A is 14, the mass must be exactly 14.0 U. But A is just a count of particles. It's always a whole number. The actual mass is almost never a whole number because of the mass defect we just talked about.
So I can't just add up the number of protons and neutrons to get the mass.
You can't.
Because I have to subtract the bit of mass that was converted to binding energy. The actual mass will always be a little less than the count. Precisely. Now, misconception number 2 is a wording trap. Students often write that mass is destroyed when a nucleus is formed. This is a huge red flag for an examiner. Mass is not destroyed. That would violate conservation laws. The correct word is converted. Mass is converted into energy according to EMCA. It's the conservation of mass energy that holds true, not just mass alone.
Got it. So I should always say the mass defect is converted into binding energy, not the mass is lost or destroyed.
Yes. That single word shows you understand the physics deeply. All right, to help all this stick, let's finish with a few memory anchors. First, a mnemonic for the symbols. A is for all the nucleons. Z defines the element. You can think of it as its identity or zeal. And N is just the number of neutrons. Next, a memorable phrase. This is the heart of the topic. Mass lost equals energy gained. The mass defect thing is the mass that became the binding energy. And finally, a physical gesture. Press your palms together really hard. Try to pull them apart, but resist. That tension you feel, that force holding them together, that represents the binding energy. The tighter the grip, the more stable the nucleus. Okay, that was our deep dive. Let's quickly summarize the 3 main factual points to remember. 1. The nucleus is the dense, positively charged core of an atom made of protons and neutrons, which are held together by the strong nuclear force. 2. Atomic masses are measured in U based on carbon-12. The fractional mass you see on the periodic table is a weighted average of an element's natural isotopes. And 3. The actual mass of a nucleus is always slightly less than the sum of its separate parts. This mass defect is converted directly into binding energy, which holds the nucleus together. To get maximum marks in 12 CBSE physics, chemistry, and maths, visit ProfSam.com.
That is ProfSam, right?
Yes, ProfSam.com. Study hard and all the best.